Hi everyone, my name's Elan van Biljon and I'm going to be telling you about my thesis that's titled Initialization of Noise Regularized Neural Networks. Alright, let's start with an overview. Previous researchers have developed network initialization techniques that have shown some good training performance. We've also seen that noise regularization allows for good generalization in neural networks. However, when we combine the two as is, we see some instability in our networks. Thus, we decided to derive a new initialization technique that seeks to stabilize this behavior. This presentation focuses on this new initialization, and since much of my contributions were in terms of empirically validating it, I focus on that as well, mostly by going through the methodology of our experiments. We also looked at searching for alternate initializations that might outperform the one we derived. However, we saw that ours is not clearly outperformed by any others, and thus recommended as a safe default for practitioners to use. So we've just gone through the outline of this presentation. Next, we'll have a look at the new initialization we derived. Then we'll have a look at how we searched for alternate initializations, and we'll look at a recap of the key takeaways of the two ideas. Within each topic, we'll look at the context of the investigation, the problem statement, how we address the problem, and the results of our experiments. Okay, let's dive straight into looking at the new initialization. There are two main things we need to understand. The first is neural networks, and the second is noise regularization. Let's start with neural networks. So neural networks are a model that learns from data. I find it easiest to first explain what they do with a few examples, and then we'll look at exactly what they are. So there have been some really cool real-world applications where neural networks have been used, such as language translation, allowing people from all over the world to connect in their own tongue. Agriculture. There's been some great applications where people have trained neural networks to detect diseases on plants and really empowered local farmers with all them really needing is a phone with a camera and access to this neural network, and then they can take care of their crops by themselves. We've also seen some applications in the energy infrastructure in terms of load balancing or saving energy for data centers and things like that. And we've seen some cool uses in healthcare. For instance, neural networks have been applied to sort of scan through various cases and give the most urgent ones to healthcare workers to look at first. Right, so what are neural networks? Neural networks are made up of what we call neurons, and this is how we represent them. A neuron takes in many inputs and provides one output. The inputs are multiplied by what we call weights. They are then summed together and summed with a bias term to form what we call the pre-activations of our neuron. The neuron is then fed through an activation function to produce the activation or the output of the neuron. This activation function is typically some non-linear function. It being non-linear enables the output of the neural network itself to be non-linear. Two popular classes of activation functions are rectifier and sigmoidal activation functions, and perhaps the most popular of each is the ReLU and the sigmoid. The ReLU clamps all negative input to 0 and allows positive input to pass unchanged, whereas the sigmoid smoothly clamps or squeezes the input to a range between 0 and 1. Right, so how do these neurons fit together to form a network? We focus on the configuration that's called a fully connected feed-forward multi-layer perceptron, and all that really means is we stack our neurons in parallel to form what we call a layer, and then we connect these layers sequentially, meaning there's no loops in the system, and we connect them in such a way that the outputs of a neuron in a previous layer connects to every input of the neurons in the next layer. Okay, so let's look at a small example. Let's say we want to sort images of cats and dogs. Our network takes them as input and produces some prediction of what class these images fall in. We then can mark these corrections as correct or incorrect, and we can assess the performance of our networks using some loss function. We use this performance to then predict adjustments to the parameters of the network, and these adjustments or gradients are calculated by optimizing the loss function. These gradients are then propagated backwards through the network to each neuron and to each relevant parameter, and then they are adjusted. One full pass of the data set to adjust the parameters is called an epoch. So before we can adjust these parameters, we need to choose some starting configuration for these parameters. This is called initialization. We know that initialization has a high impact on the final performance of a network, but we don't quite know how to predict the final performance given an initialization. We do, however, have some ideas of how we should initialize our networks. For instance, we know if we initialize our parameters to be too low, we see the pre-activations in deeper layers of the network tend towards 0. Alternately, if we initialize our parameters to be too high, we see the pre-activations explode towards infinity in deeper layers of our network. In either case, there can be some loss of information because our computers can't represent arbitrarily small or large numbers, and we call this numerical under or overflow. So what we really want is to initialize it just right, so some measure of information stays roughly constant throughout our network. We typically initialize these parameters by sampling from some random distribution, and in our work we use a normal distribution where the sigma w squared parameter controls the variance of our distribution. This forms the basis of the signal propagation method to initializing neural networks. Let's put this slightly more formally. We want the information present in our inputs to travel forward from the input to the output layer, and we want the gradient information present at the output layer to travel all the way back towards the input layer. Unfortunately, this can be tricky to predict whether this behavior will actually occur, and this is because of this nonlinear activation function that we have. So, a group of researchers decided to take a step towards solving this problem. They decided to initialize their neural networks such that they landed in this approximately linear region of this sigmoidal activation function. This allowed them to treat the network as linear and perform some analysis. They were able to look at how signals travel forward and backward through the neural network, and the specific type of information they looked at is the variance of the pre-activations. They were able to stabilize this information flow successfully. Thus, another group of researchers decided to extend this to ReLU activation functions. Next, a group of researchers decided to do away with looking at this approximately linear region and specific activation functions. They were able to develop a framework that looks more or less at arbitrary activation functions by borrowing a concept from physics called mean field theory. I'm not going into any detail in that now, but feel free to look at our papers and references to find out more about that. They looked at how information travels forward through a network, and they also looked at a new type of information called correlation information. This is basically the similarity of inputs and how they might change throughout the network. To give some intuition, we expect the correlation between the two images of the same dog to be higher than two images of different dogs, and this in turn to have a higher correlation than between an image of a dog and a cat, for instance. We also suspect that if the correlation changes throughout the network, and the correlation tends to a correlation of 1, no matter what the inputs are, we then lose some information about these inputs, and this should hinder the depth to which networks can be trained. Another group of researchers then came and extended this work again to look at how the gradients travel backwards throughout the network. So why is any of this important? Why do we really care about this? Well, we've seen that through proper initialization, we're able to train deeper networks. This graph shows two networks of the same depth. The blue is a network that has been initialized incorrectly, and the red line represents networks that a network that has been initialized correctly. We see that the red line is able to decrease its error through training, whereas the blue does not. So why do we want deeper networks? Well, historically, we've seen that as our networks have been able to grow in size and we've been able to train them effectively, we've been able to achieve better performance from these networks, and that has allowed us to apply them to some amazing real-world applications. Right, so let's look at noise regularization next. So we just said that our networks are becoming more powerful. Unfortunately, in some ways they can be too powerful. And let me show you this through an example. Again, if we want to sort through images of cats and dogs, let's say we just ask the network to draw a line that separates these two classes of images. We can see that our networks are so powerful that they could draw a line like this. For this data, this is entirely correct. It divides this perfectly well. However, if we add just a few more similar data points, we can see the network starts to make mistakes. This is what we call overfitting, and the process of preventing or mitigating this is called regularization. Essentially, we try to coax our networks to learn more general rules. One common way of doing this is through using some random noise. We might sample some noise and then alter the inputs of our neurons or network with this noise. Our work takes into account both additive and multiplicative noise. However, in this presentation, we're just going to focus on multiplicative noise. A very common form of this regularization is called dropout. It's very similar to flipping a coin. For instance, if we get heads, we might retain the input to the neuron, and if we get tails, that input might fall away. This teaches our neurons to be robust to their inputs. So why would we want this robustness? Well, an example came to mind. A group of researchers took this image of a panda and superimposed a very specifically crafted piece of noise on top of it, which produced, to my eyes, an almost identical image. However, to the neural network they presented it to, it changed its prediction from panda to gibbon with a 99% confidence. So clearly this network was not robust to this type of noise. And if our networks aren't robust to noise, it's going to be very difficult to reliably apply them to real-world applications. So we do believe that regularization is very valuable. Right, so what's the problem we want to tackle again? Using previous network initialization techniques with these noise regularization techniques can provide instability in our networks. Thus, we derived the new initialization to stabilize this behavior. We focused on the ReLU activation function, and we published this work at NeurIPS in 2018. Much of my contributions were in the form of empirically validating our theory, so let's look at how we did that. We looked at two types of information flow, variance and correlation, and let's start with variance. First, we generated some inputs of known variance. We then propagated these inputs through the network and tracked how the variance changes. We then also did so for two real-world data sets and also looked at how deep this variance information travels. The two data sets we looked at were CFAR10 and MNIST. In terms of correlation, we very similarly generated inputs where the correlation between the inputs was known. We then propagated these inputs through networks and tracked how the correlation between these changes throughout the network. Because we suspect the depth to which correlation information to heavily impact the depth to which networks can be trained, we also trained networks on these two datasets for 200 epochs on an image reconstruction task. Because we wanted to investigate the relationship between performance, initialization, and depth, we conducted a grid search over these parameters and trained 100 networks per dataset. Right, so let's have a look at some of these results, starting with variance. Let's look at the theory first. On the left, we see how variance changes across successive layers of the network. In other words, what is the variance at the input of a layer versus the variance at the output of a layer. On the right, we see the variance at specific layers of the network. For instance, what's the variance at layer 8? On the left, we see that our initialization provides networks that run along the unity line, meaning that if our input has a variance of 4, then the output of that layer will also have a variance of 4. On the right, this results in a line that has constant variance throughout the network. On the left, initializations other than ours either provide networks above or below the diagonal, resulting in exploding or vanishing variance throughout the network. Let's see how our empirical measurements align with the theory. The means are represented by dots, and the shaded regions represent the one standard deviation bound. So we see very good alignment between our theory and measured values. Next, we looked at how deep the variance information can travel based on the precision of the computers that we are running the experiments on. The cyan line predicts the depth to which we expect information to propagate, and the black regions show the regions of numerical instability. The black dashed line represents our initialization, and the other dashed lines represent previous common initializations. Remember, we performed this experiment for both datasets, and we plotted the variance as a heat map. We again see some good alignment between our prediction and the actual depth to which variance information traveled, and we see that our initialization stabilizes variance information to arbitrary layers in the network, whereas the other two initializations lead to instability at some point. Looking at correlation information and starting again with the theory, on the left we see how correlation changes across successive layers of our network, and on the right we see how correlation changes throughout the layers of our network. On the left we see all curves either increase or decrease to a fixed point, these crosses, and we see that these crosses or fixed points depend on the amount of noise being injected to the network. Let's see how this aligns with our empirical measurements. Again, we see some very good alignment. Now we can look at some conclusions from this. On the right, if we look at the blue lines that represent networks without any noise, we see that no matter what the correlation of the inputs are at the input layer, they all tend to a correlation of 1 at some depth, meaning that, like we said before, we lose some information of how to distinguish these inputs. We see that as we inject noise, that we no longer tend to a correlation of 1. However, this is simply due to the fact that we're injecting independent random noise. We also see that the point at which the lines meet happens at earlier layers for higher amounts of noise that's being injected. So we suspect that the depth of our networks will be more limited with higher amounts of noise regularization. To test this, we plotted our theoretical boundary that separates the trainable and untrainable regions. We then trained 100 networks on each dataset with the grid search that we mentioned before, and we plotted the test loss as a heat map. The red region indicates networks of poor performance, and the blue region indicates networks of better performance. And we see this line separates these two regions quite well. This again reinforces that low amounts of noise regularization allows us to train deeper networks, whereas high amounts results in only shallow networks performing effectively. Right, so what are the two key takeaways from this work? We recommend the use of our initialization as it stabilizes some information propagation, and we recommend that one limit the depth of one's network according to the noise regularization strength being used. Right, so let's look at how we search for alternate initializations. We're going to look at the context and the problem statement together because it's quite brief. So remember, we predicted that we could propagate variance information arbitrarily deep through our networks. We also recommended limiting the depth of one's network. If we do this, we create this window of viable network initializations that all lead to numerically stable information propagation. Thus, we wanted to investigate if any of these initializations might outperform ours, and we took inspiration from the randomized controlled trial. In medicine, if one wants to test the effectiveness of various drugs on a population, we divide our population into groups and test our drug on each group, and we have a group for a placebo, because humans are susceptible to the placebo effect. However, in our case, we are using neural networks, so we can do away with this placebo group, and we no longer need to divide our population. We can duplicate our networks and test each intervention on each neural network. Again, we searched this region using a randomized controlled trial, and we published this study in Pattern Recognition Letters in 2020. So let's look at how we conducted the study. We conducted a randomized controlled trial, the first step of which being to define our interventions, the second step being to generate our models. We then duplicated these models and paired each duplicate with an intervention. We then trained all our networks and analyzed the results. So let's look at how we define our interventions. We wanted to compare our initialization to others. So the first intervention would be our initialization. We then created a group of initializations to the left of ours, calling them the L group. We spaced them closer to each other the closer they were to our initialization, because we assumed more interesting behavior to occur here. And we then reflected this group about our initialization to form the R or right group. Because we saw there was still some more space on the right, we then added 2 more initializations, calling them the extreme initializations. This created a group of 11 interventions in total. Next, we generated our models. We created a population size of different models we could sample. We did so by varying certain hyperparameters within a range. The first hyperparameter we allowed to vary was the dropout rate. Next was the data set, then batch size, learning rate, optimization and momentum, and finally the topology of our network in terms of width and depth. All hyperparameter ranges were in line with what practitioners would typically use and according to our theory. In other words, our networks were slightly wider than is typical and were of constant width. This created a population size of roughly 100,000 neural networks, of which we sampled 1,000. We would have liked to sample more, but we'll see in a few slides why that was not feasible. Even so, we expect the results obtained on the subsample to generalize to the greater population. We hope that the results seen on the sample would also generalize to hyperparameter spaces outside of what we searched, but we cannot guarantee that. We then duplicated the sample 11 times, one for each initialization, and we then trained all 11,000 neural networks for 500 epochs on a classification task. This shows why we were only able to sample roughly 1,000 networks. Even though we used a cluster of 30 computers, we were competing with a heavy load shedding schedule and other demands on the cluster. Next, we'll analyze the performance of these various interventions. We performed hypothesis tests and calculated effect sizes. However, these results are quite difficult to present in this presentation, so we're going to focus on visual interpretations. So let's look at those results. We looked at 3 different measures of performance, starting with test accuracy. We define this as the best test accuracy achieved throughout training for each network, and higher is better. We looked at training time, the epoch at which this test accuracy was achieved, and lower is better. And we looked at generalization gap, the difference between the best test accuracy and the best training accuracy for each network, and lower is better. Remember that we used initializations as our intervention. However, we did frame our methodology in a way that allowed us to look at the results through the perspective of having used noise regularization as our intervention, and we're able to divide results based on data set. So let's look at the test accuracy distributions divided by initialization. On the left, we see the labels of each distribution for initialization. On the horizontal axis, we see the accuracy values. The black dotted lines represent modes of these distributions, and the number to the right represents the rank of this mode, 1 being the highest, 2 being the second highest, and so on. The white and gray dotted line represents the means of these distributions. So we can immediately see that these initializations have some mass at high accuracy values, whereas the extreme initializations have almost all their mass at very low accuracy values. Thus, we can see the extreme initializations perform very poorly in general, and we eliminated them from further study. Even so, we saw there were a few modes present in our distributions, and we suspected this is due to the mixing of results in different data sets. Thus, we divided our results based on data set and picked the one that looked most representative. So we ended up using CFAR10. So looking at the test accuracy distributions divided by initialization on the CFAR10 dataset, we can see the following. Our means form a U shape that peaks around our initialization, meaning that our initialization provides perhaps higher typical performance than the other initializations. We see the modes are very roughly in line with each other, perhaps peaking slightly towards the left initializations. However, we see higher mass present at low accuracy values for the left initializations. In terms of training time, we see very little difference between initializations. However, we do see a limitation of our work present here. We see that many networks were still improving in test accuracy when training was halted. Thus, very few networks have converged, and this impacts the strength of our results on previous and future slides. If we could go back, we would first conduct a study that looked at how many epochs we would need for our networks to converge on each data set. In terms of generalization gap, we again see very little difference between our initializations. Right, so let's next look at the results through the frame of using noise regularization as the intervention. Looking at test accuracy distributions divided by dropout rate, this blue group is the group of networks that have no dropout, and we see it has the highest typical performance. We see that typical performance decreases as we increase our dropout rate, and this leads to an interesting phenomenon where if a practitioner is only able to train one network, we suggest they not use dropout, whereas we see the groups of moderate levels of dropout lead to higher modes and higher best performing networks. Thus, if practitioners have time to retrain models or train multiple models, we recommend using moderate levels of dropout as they might provide the best performing networks. We see the group of a dropout of 0.5 provides the worst typical performance, and a mode and best performing networks roughly in line with a dropout of 0. These results may have changed if we allowed our networks to train for longer or to convergence, however. In terms of training time, we see an increase in training time with an increase in dropout rate, which is not very surprising as the networks need to learn to perform the task through noise. In terms of generalization gap, we see a decrease in generalization gap with an increase in dropout rate, which is again not surprising as this is almost the goal of regularization. So what are the two key takeaways of this work? First, we can recommend our initialization as a safe default, as no other initializations clearly outperformed it. Next, we recommend that one limit the amount of noise regularization being used to little or no dropout. Right, so let's look at the key takeaways of both works together quickly. Again, we recommend the use of our initialization. We recommend one limit the depth of your network according to the dropout strength or regularization strength being used, and we recommend moderate to no levels of noise regularization depending on your use case. So this work took many years to complete, and I would just like to thank a few people that made this possible, starting with my supervisor, Professor Steve Kroon, and then with my two co-authors, Arnu and Herman. Thank you so much for all your support. These institutions also greatly supported me throughout my work, so I'd like to thank you as well.